Welcome to this explainer. Right now, we are living through an absolute boom in AI development tools. I mean, agents are getting faster, smarter, and just incredibly capable. But there's a massive double-edged sword here. When you give an AI actual power to execute code on your machine, you're basically handing over the keys to your entire system. So today, we're going to learn exactly how to lock that system down without sacrificing the incredible speed these agents provide.
Okay, let's run through our technical blueprint for today real quick. We're covering the autonomous agent threat, the propose and dispose model, our 5 tiers of reversibility, provable guarantees versus mitigations, and finally, integrating the governance layer. All right, jumping right into Section 1, the autonomous agent threat.
Seriously, I want you to ask yourself right now, what actually happens if your coding agent just decides to delete your entire project? Imagine grabbing a quick cup of coffee. You come back, and your agent has hallucinated some recursive delete command on your main branch. It sounds crazy, right? But this isn't just some theoretical risk. It is the fundamental danger of giving an untrusted intelligence completely unfettered access to your system. We want the AI to work at light speed for sure, but we also live in absolute terror of it making a catastrophic error. That tension, that's exactly what we have to solve.
So, to solve it, we first have to get really clear on what we're dealing with. We're talking about an untrusted autonomous agent. That's a highly capable AI given shell and file system access that can inadvertently destroy work or maliciously exfiltrate private data if it doesn't have a definitive boundary. Now, we give them this access because they literally need it to compile code, run tests, build things. But doing this without boundaries, it's like handing the keys to a Ferrari to someone who only just found out what a road is. We absolutely cannot allow irreversible catastrophe.
Moving right along to Section 2, the propose and dispose model.
The architectural fix for this threat is something called the runtime assurance pattern. And honestly, the way it solves the permission problem is brilliant. The agent never actually touches the machine directly. It's completely separated. Think of it kind of like an airlock on a spaceship. Nothing gets through to the critical systems without explicit clearance. The agent only ever proposes an action, while a separate, absolutely trusted governance gate actually disposes of that proposal.
So this breaks down into a really strict 3-step checkpoint. First off, the untrusted agent proposes an action. Picture a super eager junior developer writing some code. Second, the trusted gate disposes of it, judging the risk exactly like a strict senior architect reviewing a pull request before it merges. Third, the action is either blocked entirely, escalated to a human, or confined to run safely within the workspace. Every single shell command is intercepted and judged so that it only ever runs in a safely padded room.
Which brings us to Section 3, 5 tiers of reversibility.
So how does that gatekeeper actually make the call? Well, the system evaluates every single proposed action against exactly 5 strict levels of escalation. And why 5 strict levels? Because, let's be real, when your proprietary data and core infrastructure are on the line, you can't just rely on AI vibes or LLM guessing games. You need a rock-solid deterministic rulebook that behaves exactly the same way every single time.
Let's break these tiers down, because they're extremely logical. Tier 0 and 1, those cover your reversible or semi-reversible tasks. Reading a file, running tests, making a local git commit. You just let those fly automatically. Tier 2 introduces a bit of friction for protected operations, like a pip install, since that actually alters the environment. But Tier 3 is where things get serious. Irreversible actions, like a force push. Those stop and require a manual human approval token. Finally, Tier 4 is a hard block for anything trying to escape the workspace entirely, like network egress or using sudo.
If you strip all of this down to its core, the entire governance layer hinges on one remarkably simple question. Can this action be undone? Take a moment and let the weight of that sink in. Reversibility is the absolute perfect security anchor. It completely cuts through the noise of millions of possible commands and translates this massively complex threat landscape into a universal focus on what can permanently hurt you.
The foundational documentation spells this out perfectly. Higher tier equals harder to undo equals higher bar to allow. Basically, this means the rules are strictly monotonic. They only go in one direction. It is mathematically impossible for a highly destructive, high-tier action to somehow slip through a lower security loophole. It acts as a one-way ratchet of security.
Okay, Section 4, provable guarantees versus mitigations. I really love the radical honesty of this framework because it splits everything into 2 distinct halves. On one side, we have the provable envelope. The actual core gate logic is proven correct via Z3 proofs. For the non-math folks out there, a Z3 proof is a literal mathematical guarantee. It cannot be tricked. On the other side, we have mitigated recognition.
Catching tricky, obfuscated shell commands is handled by a classifier that was absolutely bombarded with fuzzed inputs during testing. It's built to fail closed, meaning if it ever gets confused, it instantly escalates the tier to keep you safe.
Let's get explicitly clear about what this fortress actually stops. It stops the agent from trashing your files, it stops it from reaching outside the designated workspace, no exfiltrating your private source code over the network, which, let's face it, is the ultimate nightmare. It blocks privilege escalation, and it catches known obfuscated bash tricks where someone might try to sneak a script past a basic string filter. It excels at forcing any irreversible action to just hit pause.
But conversely, what is completely out of scope? Well, this layer will not stop kernel exploits. Handling those is the job of your underlying operating system. It definitely doesn't guarantee the code your AI writes is bug-free, and it won't catch a patient, low and slow attacker who is perfectly mimicking normal behavior. We have to be transparent here. This is a policy gate that governs reach. It is meant to be layered on top of your existing container security.
Let's bring it all together in Section 5, integrating the governance layer.
Now, you might be thinking, okay, a mathematically proven system? That sounds heavy, bloated, and awful to install. But the reality is incredibly lightweight. It's written in the pure standard Python library. 0 runtime dependencies for the core gate. That is huge because developers absolutely despise having to install 50 bloated packages just to secure a single agent. It simply drops seamlessly over your existing sandbox setup.
Looking at how this actually wires into a real agent loop, it's remarkably clean. You essentially just initialize a governor, point it at your specific workspace path, and set your autonomous limit, like Tier 1, for example. Then you just wrap the agent's execution phase. You are intercepting the agent's output right before it runs, passing it to the governor, and asking for a verdict. It's literally just a few lines of code to secure the whole shebang. From there, the governor shoots back one of 4 explicit verdicts. Allow means go ahead, deny stops it cold, but, and this is super important, it feeds the error reason back so the AI can actually learn and correct itself. But the real magic is an ask human or needs grant. Instead of just crashing your application, the agent gracefully pauses. It waits for a human review token, exactly like a polite assistant asking for a signature before mailing a critical letter. So, as we wrap up this explainer, I really want you to take a hard look at your current AI deployment and ask yourself a slightly uncomfortable question. Is your autonomous agent truly governed, or are you just getting lucky? True governance isn't crossing your fingers and hoping the AI behaves. It's mathematically proving that it has to. The era of just hoping for the best is over, my friends. Go check your deployments, ensure your layers are secure, and keep building safely.